we're going to consider the problem of finding the inverse of a matrix if it exists. First, we'll look at inverse matrices of elementary matrices. Recall that there are three types of elementary matrices corresponding to the three types of elementary row operations. The relationship between an elementary row operation and its corresponding elementary matrix is as follows. If you start with a matrix A and perform one of these elementary row operations, it's the same as multiplying to the left of A by the elementary matrix that corresponds to the elementary row operation that you have performed. Now let's consider each of these elementary row operations in turn. Suppose that my elementary matrix corresponds to the elementary row operation of adding alpha times row j to row I. And so what we want is a matrix that corresponds to the action of undoing this operation. So if we have added alpha times row j to row I, to undo that, we can take minus alpha times row j and add it to row I. So for example, this is the elementary matrix of taking 7 times row 1 and adding it to row 2. And the inverse of this is simply changing the 7 to a minus 7. Now suppose that my elementary matrix corresponds to swapping row I and row j. Well, if you do that twice in a row, basically you have done nothing. So the elementary matrix that corresponds to this operation is its own inverse. For example, this is the matrix that corresponds to interchanging row 1 and row 2. And its inverse is the same as itself. And finally, if we look at the elementary matrix that corresponds to multiplying row I by a non-zero scalar alpha, we can undo that by multiplying row I by the multiplicative inverse of alpha. For example, this is the elementary matrix of multiplying row 2 by 2, and its inverse is simply changing the 2 to 1/2. Let's now look at a procedure for finding A inverse, where A is an n by n matrix with entries from a field F. What we need to find is an n by n matrix B such that A times B is the n by n identity matrix. So we're trying to find a right inverse of A, but remember that a right inverse is also a left inverse. So if B satisfies this equation, then B is the inverse of A. If we look at this matrix equation a bit further, we can expand it as follows. So the product can be written as A times the first column of B, that is the first column, and the second column is A times the second column of B, and so on, up to A times the nth column of B, and this has to equal the first column of the identity matrix all the way up to the nth column of the identity matrix. In other words, we want B to be such that this is equal to E1, this is equal to E2, and this is equal to En. So in effect, we are trying to solve all these n systems of linear equations at the same time. And we can do that by forming the extended augmented matrix and row reduce this until we get something that is in reduced row echelon form. And if we end up with something that looks like this, then B will be the inverse of A. Now, if the first n columns do not give an identity matrix, then we can say that A is not invertible. And so let's look at an example. Here we're going to take a 2 by 2 matrix with entries that are complex numbers. So as mentioned before, we form the extended augmented matrix, and there's this matrix here. Multiplying row 2 by a half, we get this. And now adding minus I times row 2 to row 1, we get this. And since the first two columns give the 2 by 2 identity matrix, this will be A inverse.